All right, acid-base titrations. Uh, in this type of titration, what we're going to be titrating into is something of known concentration. And what we're going to be looking at is the change in pH. It's different than the other one we did where we didn't know what the concentration of the unknown was, and we were using a known to find an unknown. What we're interested in with these titrations is how the pH is affected. All right, so as the last time, right, the equivalence point is a point during the titration where I've added enough moles of the titrant to burn up moles of things I'm titrating into. And we use some sort of acid-base detector or some sort of electrical device to indicate that point. So how does the pH change during the course of the following titrations? And what we're going to do is titrate a strong acid with a strong base, a weak acid in a strong base, and a weak base in a strong acid. All right, so we're going to look at these three different types of titrations and how they're treated. So the easiest one is strong acid and strong base. When we do a strong acid, strong base titration, it's just a neutralization reaction. It's very spontaneous. So really what it is recognizing what the limiting, what's in excess actually, in terms of what's affecting the pH. So I'm going to titrate 25 milliliters of 0.1 molar hydrochloric acid, right? That's what's in my beaker. And what I'm going to add to that is 0.1 molar sodium hydroxide, the base. All right, millimoles per milliliter is the same magnitude of ratio if you have moles per liter, right? Milli just means a thousandth. So if I divide a thousandth of a mole by a thousandth of a liter, I get the same ratio if it's mole per liter. So sometimes it's easier to do these problems in terms of millimoles. So what is the pH after the addition of 10 milliliters to a 0.1 molar what's the pH after the addition of 10 milliliters of 0.1 molar sodium hydroxide to 25 milliliters of 0.1 molar hydrochloric acid? So if I can give it milliliters in the molarity, I can multiply milliliters by molarity and get how many millimoles of each of these I'm reacting. So if I have 10 milliliters of a 0.1 molar solution, I've got 1 millimole. If I've got 25 milliliters of 0.1 molar solution, I've got 2.5 millimoles. And frankly, these are easier to deal with than moles at this point because we're dealing with fractions. So it's easier this way. So if I have 2.5 millimoles of hydrochloric acid and 1 millimole of sodium hydroxide, the hydrochloric acid is in excess, right? I'm only going to burn up a little bit of the hydrochloric acid to make water. So it goes all the way forward. I go to 0 with the hydroxide, which is limiting, and I lower my H plus concentration, my hydrochloric acid concentration, in other words. So what's left in the beaker affecting the pH is that leftover hydrochloric acid. So I've got 1.5 millimoles, and my new volume, since I've added 10 milliliters to 25 milliliters, is 35 milliliters. So milliliters to divide into millimoles gives me the concentration of H plus in terms of moles per liter. Take the negative log and get the pH at this point. All right, so the pH after adding that much base is now 1.37. If I add 25 milliliters of the 0.1 molar sodium hydroxide, I'm adding 2.5 millimoles of reacting 2.5 millimoles of the hydroxide with 2.5 millimoles of the H plus ion. So this is the equivalence point, right? I've got the same number of moles of acid as base, so it goes to 0, and all I'm left with in the water is water. All right, so the only thing that's producing H plus ion in the water is the autoionization of water, right, which gives you an H plus concentration of 10 to the negative 7. So take the negative log and you get a pH of 7. So when we're dealing with a strong acid, strong base neutralization, the equivalence point is 7 every time. So initially I had a 1 molar concentration, and then I added my 10 millimoles of, I had a pH of 1 initially with my 0.1 molar hydrochloric acid solution. And now I added 10 millimoles of the base, and now the pH went up a little bit, but not much. A little more, and then boom, big jump. Right? When you hit the equivalence point, you jump up to 7. So when I plot these points, pH versus the volume of sodium hydroxide added, I get a big jump at the equivalence point, right? Burning up the acid, boom, acid burned up. Now my next drop is just going to be pure sodium hydroxide at this point. So in excess will be the hydroxide, right? So if I add 35 milliliters of 0.1 molar sodium hydroxide, 2.5 millimoles of hydrochloric acid in the beaker. I add my 3.5 millimoles of hydroxide. I have 1 millimole of hydroxide left. So that's the main thing in the beaker affecting the pH, all that hydroxide that's left over. So divide that by the total volume, right? 35 milliliters plus 25 milliliters is 60 milliliters. Divide into my millimoles of hydroxide and get the concentration of the hydroxide. So to get the pH at this point, you take the negative log and get the pOH. Subtract from 14 to get the pH. So if I plot these points, all right, past the equivalence point, the pH shoots way up and then it starts tapering off again, right? The pH doesn't keep going up and up and up. It's because I run out of H plus ion, right? The H plus ion concentration is down to 10 to the negative 15 when you're up at a pH of 15. So it's hard to find at this point. So notice the shape of this titration curve. This is what this is called. pH slowly goes up and then big jump up when I hit the equivalence point. And then a big jump up past the equivalence point and then it tapers off again. So what I end up with a strong acid, strong base titration curve is a symmetrical curve where the equivalence point has a pH of 7. And that's the same for all strong acid, strong base titration curves. I could titrate the other way. I could have a beaker full of base and titrate strong acid into it. It's the same type of titration, it's just the other way. So you're starting out with a very low H plus concentration, right, a pH of 15. And as I add my hydrochloric acid, burning up the hydroxide, use up all the hydroxide at the equivalence point, and then just start adding pure hydrochloric acid so the pH goes way down. So it's again a symmetrical curve, except you're starting at a very high pH and going to the low pH.